Welcome to the deep dive. Today, we're diving into the world of semiconductors.
Oh, cool.
Those tiny but super important components that are in like practically everything these days,
Yeah, they're everywhere.
Smartphones, cars, pretty much all modern electronics.
Absolutely.
You sent in Cracking the Code of Semiconductors by Bergeron and Spencer.
Oh, great book.
And
Yeah.
I gotta say, it's a really fascinating read.
Yeah, it's a good one.
We're gonna break down the science behind these little wonders and really try to understand why they're so essential to our modern lives.
Yeah, it's amazing how something so small can have such a huge impact.
Right. Most people probably don't even realize how reliant we are on these tiny little things.
Exactly, it's true.
And Bergeron and Spencer, actually, they make that point right from the start of the book.
Oh, yeah.
They quote Intel CEO Pat Gelsinger, who says that semiconductors are basically the brains of modern electronics and that they're shaping the future of the global economy.
Wow, no pressure then, right?
No pressure. Yeah, no big deal.
They're truly essential for pretty much every industry you can think of.
Oh, yeah, definitely.
But the cool thing is, as complex as the technology is, the authors do a fantastic job of breaking it down in a way that's easy to understand.
They really do, yeah.
Yeah.
Before we get into the nitty-gritty of how semiconductors actually work, I'm curious to learn a bit more about the people behind this book,
Sure.
what sparked their passion for this field.
Yeah, for sure. Let's start with Diana Bergeron.
Okay,
Her journey is really quite inspiring.
okay.
She started out in electrical engineering,
Uh-huh.
and now she's a leading expert in semiconductor technology at the University of Toronto.
Wow.
But what I find really interesting is that she's also an avid sailor and photographer.
Oh, wow, that's cool.
Yeah, it's always neat to see experts with these diverse interests.
Yeah, absolutely.
It definitely paints a picture of someone who's curious and engaged with the world.
Yeah, for sure.
And then we have her co-author, David Spencer.
Okay.
He grew up in Cape Town, South Africa, and was fascinated by electronics from a really young age.
Oh, wow.
He followed that passion all the way to becoming a renowned semiconductor engineer and physicist.
So from like tinkering with electronics in Cape Town to becoming a leading expert, that's quite a journey.
It is. It is.
It seems like both authors share this belief that semiconductors have the potential to really improve our lives.
They absolutely do.
Yeah.
And that comes through in their writing.
Yeah.
They see semiconductors as key to innovations in medicine, communication, energy,
Wow.
you name it. It's that
Oh,
kind of
yeah.
vision that really drives progress.
Yeah, absolutely.
Yeah,
Okay, so we've got these brilliant minds behind the book,
we do.
and now it's time to delve into the science a bit.
Okay, feels good.
What exactly are semiconductors and what makes them so special?
So you can think of them as kind of like the middle ground
Okay.
between conductors, which let electricity flow freely,
Uh-huh.
and insulators, which block that flow.
Okay.
Semiconductors can do a bit of both,
Oh, interesting.
and that's where things get interesting.
Interesting indeed.
Yeah,
The book mentions silicon as the most common semiconductor material.
it is, yeah.
But how does something like silicon, which we usually think of as sand, become the backbone of all this modern electronics?
It all comes down to how electrons behave within these materials.
Okay.
So electrons in an atom, they can only exist at specific energy levels,
Okay.
kind of like steps on a staircase.
Okay.
In conductors, these energy levels overlap, allowing the electrons to move freely.
Okay.
In insulators, there's this large gap between the levels,
Mm-hmm.
making it really hard for electrons to jump across.
So conductors are like smooth escalators for electrons, and insulators are like a giant wall.
Exactly, that's a great analogy.
Where do semiconductors fit in?
Semiconductors have a smaller gap between those energy levels.
Okay.
Think of it like a small step that electrons can sometimes jump across,
Uh-huh.
but not always.
Okay.
And here's the key.
Yeah.
We can actually manipulate that gap by adding impurities to the semiconductor, a process called doping.
Oh, so by adding impurities, we're basically controlling how easily those electrons can move through the material.
Exactly, that's it.
That's pretty clever.
Yeah, it is. And by controlling that electron flow, we can create all sorts of electronic components like transistors,
Yeah.
which are the building blocks of modern electronics.
Okay.
Silicon's the most common because it's abundant.
Makes sense.
And we've gotten really good at manipulating its properties.
Okay.
Yeah.
But the book also mentions germanium, right?
Yes, it does.
What's the story there?
Germanium was actually used in some of the earliest transistors,
Oh, really?
and it has some advantages over silicon,
Okay.
like higher electron mobility.
Okay.
This means that the electrons can zip through it faster,
Uh-huh.
which is great for speed,
Okay.
but germanium is also more sensitive to heat,
Oh, okay.
which can limit its use in certain applications.
So it's a trade-off.
Exactly.
Silicon's like the workhorse.
It is.
But there are other materials with their own strengths and weaknesses.
Yeah, definitely.
And speaking of other materials, the book dives into something called compound semiconductors.
It does, yeah.
What are those all about?
Compound semiconductors are made from combinations of elements,
Okay.
often from groups 3 and 5 of the periodic table.
Okay.
These materials have unique properties that make them ideal for specialized applications.
Okay, so they're like the specialty ingredients in the semiconductor world.
Yeah, I like that.
Give me some examples.
Okay, so you've got gallium arsenide, or JAs for short.
Okay.
It's got this amazing ability to convert electricity directly into light.
Oh, wow.
And it's used in everything from LEDs and lasers to high-frequency communication systems.
So JAs is the light bringer.
I like it, yeah.
What about other compound semiconductors?
Then you have silicon carbide, or SiC.
Okay.
This material is incredibly tough.
Uh-huh.
It can handle much higher voltages and temperatures than silicon.
Wow.
It's finding its way into electric vehicles, power grids, even aerospace applications.
So SiC is like the superhero of semiconductors.
Yeah, exactly. You can really handle the tough stuff.
With all this talk about materials, I'm starting to see just how versatile semiconductors really are.
Yeah, they really are.
But how do these materials actually become the electronic devices that we use every day?
That's where things get even more fascinating.
I bet.
In Part 2, we'll explore the world of integrated circuits.
Okay.
Those tiny chips that pack billions of transistors onto a single sliver of silicon.
It's hard to even imagine.
It is. It's mind-blowing.
We'll discover how these circuits have revolutionized electronics and how engineers are constantly pushing the limits of miniaturization.
It's amazing what they're able to do.
I just can't wait to dive into that.
Yeah, it'll be fun.
Absolutely.
Welcome back to our deep dive into the world of semiconductors.
I'm ready to dive even deeper.
So before we jump into all the intricacies of these integrated circuits,
Okay.
let's unpack one of the most fundamental structures that makes all of this magic possible. The MOS structure.
Yeah, yes. The MOS structure, the book mentions that this is like the foundation for MOSFETs,
It is.
which sound like the superstars of the semiconductor world.
They are pretty important.
But I have to admit, I'm still a bit fuzzy on what MOS actually stands for and how it works.
Okay, sure.
Yeah.
So MOS stands for metal oxide semiconductor.
Okay.
And it's essentially a carefully crafted sandwich of materials.
Okay.
You have a metal gate electrode on top,
Okay.
a thin layer of silicon dioxide as the insulator in the middle,
Uh-huh.
and a semiconductor substrate, usually silicon, at the bottom.
Okay, so we've got our semiconductor sandwich.
Yeah.
But how does this simple structure lead to something as complex as a transistor?
Well, the magic lies in how these materials interact with electric fields.
Okay.
Imagine applying a positive voltage to that metal gate.
Okay.
What happens is it attracts electrons to the surface of the semiconductor below,
Okay.
creating a conductive channel that allows current to flow.
So it's like the gate is controlling this pathway for the electricity to flow through.
Exactly.
But how does it actually switch the current on and off?
That's where the concept of a threshold voltage comes in.
Okay.
It's the minimum voltage needed on the gate to create that conductive channel.
Uh-huh.
Below this threshold, the transistor's off,
Okay.
and no current flows.
Okay.
But once you hit that magic number,
Yeah.
boom, the channel opens up and electricity can flow between the source and drain regions of the MOSFET.
It's like a tiny little gatekeeper controlling the flow of electricity.
It is. It's a great analogy.
And the book mentioned that shrinking the size of these transistors has been crucial for improving performance.
It has, yeah.
Why is that?
As transistors get smaller, that insulating oxide layer in the middle, it gets thinner.
Okay.
This means that the gate can exert more control over the channel with less voltage,
Okay.
leading to faster switching speeds and lower power consumption.
So smaller means faster and more efficient.
Exactly.
It makes sense why there's this constant push for miniaturization.
Right.
But is there a limit to how small you can make these things?
That's a great question, and it leads us to the challenges of scaling.
Okay.
As we shrink transistors down to the nanometer scale,
Mm-hmm.
some interesting things start to happen.
Okay.
For instance, you can get something called leakage current,
Okay.
where electricity starts to seep through even when the transistor is supposed to be off.
Oh, that doesn't sound good.
No, it's not ideal.
It's like the gate is losing its grip on the flow of electricity.
Right.
So how do engineers solve this problem?
Innovation.
Oh,
They've come up with incredibly clever designs
yeah.
to maintain control of these tiny scales.
Uh-huh.
The book highlights FinFETs as one of the major breakthroughs.
Okay.
Picture this. Instead of a flat channel,
Okay.
the channel is shaped like a fin sticking up vertically.
A fin, like on a fish.
Exactly.
Okay.
And the gate wraps around this fin,
Huh.
providing better control over the channel and reducing leakage.
Okay.
It's like having a three-sided grip instead of just one.
Ingenious.
It is pretty clever.
It seems like engineers are constantly coming up with new ways to outsmart these limitations.
They are. It's amazing.
The book also mentions something called FDSOI transistors.
Yes.
What's that all about?
FDSOI stands for fully depleted silicon on insulator.
Okay.
It's another clever approach to minimizing leakage.
Okay.
Imagine a thin layer of silicon, like a tiny island, sitting on top of an insulator.
Okay.
This isolation helps reduce leakage and enables faster switching, making it ideal for low-power applications.
So it's like creating this protected zone for the transistor to operate in.
Exactly. That's a good way to think about it.
And then there are the GAA transistors, which sound even more advanced.
GAA stands for gate all-around.
Okay.
In these transistors, the gate completely surrounds the channel,
Wow.
offering even better control and potentially pushing the limits of miniaturization even further.
Okay.
It's still early days,
Uh-huh.
but GAA transistors are definitely a hot topic in semiconductor research.
From a flat sandwich to a fin to a fully enclosed channel.
Yeah, it's amazing.
It's amazing how transistor designs have evolved.
It really is.
But the world of transistors isn't just about MOSFETs, is it?
It's not.
The book also talks about BJTs.
Yes, it does.
BJTs, or bipolar junction transistors, are another type of transistor
Yeah.
that are still widely used today.
Yes, definitely.
Especially in applications that require high current handling capabilities.
Exactly.
They work a bit differently than MOSFETs,
Hey, do
relying on the flow of both electrons and those positively charged holes we discussed earlier.
That's right.
Okay, so MOSFETs and BJTs are like two different approaches to controlling current flow.
Yes.
What are the key differences between them?
Well, one key difference lies in how they control that current.
Okay.
MOSFETs are voltage controlled, meaning the voltage on the gate determines the current flow.
Okay.
BJTs, on the other hand, are current controlled,
Okay.
meaning a small current injected into the base region triggers a much larger current flow between the emitter and collector.
So MOSFETs are like precise gatekeepers?
Yes.
While BJTs are more like amplifiers. It sounds like they each have their own strengths and weaknesses.
They do, for sure.
Exactly.
MOSFETs are incredibly efficient
Uh-huh.
and dominate in low-power and high-speed applications,
Yeah.
like those found in computers and smartphones.
Yeah.
BJTs, on the other hand, excel at handling high currents
Okay.
and are often used in power amplifiers and certain analog circuits.
So it's not about one being better than the other.
Sure.
It's about choosing the right tool for the job.
Exactly.
But with all this talk about transistors,
Yeah.
I'm curious about how they're actually put together to create the electronic circuits that power our devices.
That brings us to the world of integrated circuits, or ICs,
Yeah.
which are essentially entire circuits built on a single chip.
Okay.
And that's where the real magic of miniaturization and complexity comes in.
Okay, so we're back and ready to explore those integrated circuits, those ICs.
Yeah, the heart of modern electronics.
You hinted that these tiny chips are where the real magic happens, packing billions of transistors onto a sliver of silicon.
It's really quite remarkable.
That's mind-boggling.
It is. The scale of integration is incredible.
The book talks about different types of ICs, like analog, digital, and mixed signal.
Right.
What's the difference between those?
Well, analog ICs, they're designed to process continuous signals, things like sound and light. They're used in amplifiers, filters, sensors.
Mm-hmm.
Digital ICs, on the other hand, deal with discrete signals, the ones and zeros that make up digital data.
Okay.
They're the brains behind microprocessors, memory chips, all things digital.
So analog is for the real world and digital is for the computer world.
That's a good way to think about it.
What about mixed signal ICs?
Mixed signal ICs, they bridge the gap between the analog and digital worlds.
Okay.
They handle both continuous and discrete signals, making them essential for devices that interact with the physical world, like smartphones and digital cameras.
It's fascinating how these different types of ICs all work together to create the devices we rely on.
It really is a marvel of engineering.
Earlier, we were talking about compound semiconductors, like gallium arsenide and silicon carbide.
Yeah.
Do they play a role in ICs as well?
Absolutely. While silicon is the workhorse for most ICs,
Uh-huh.
compound semiconductors are finding their way into more specialized applications.
Okay.
especially those that demand really high speed or high power.
The book mentioned something called HEMAs, which use these compound semiconductors.
Yeah.
What makes them so special?
HEMTs, or high electron mobility transistors.
Okay.
They're designed to take advantage of the incredible speed at which electrons can move through materials like gallium arsenide.
Okay.
They use a clever trick called a heterojunction, which is basically a boundary between two different semiconductor materials.
Another semiconductor sandwich.
You got it.
I'm sensing a theme here.
This heterojunction creates a region where electrons can move with very little resistance,
Okay.
kind of like an electron superhighway.
Oh, wow.
This makes HEMTs incredibly fast, perfect for things like 5G communications, satellite communications, even radar systems.
So whenever I'm streaming a video on my phone, there's a good chance a HEMT is working behind the scenes to make that happen.
It's very likely, yes.
They're the unsung heroes of our high-speed interconnected world.
They really are.
And speaking of data, we can't forget about memory devices.
Right.
You know, those essential components that store all our information.
Absolutely essential.
The book delves into different types of memory, like DRAM, SRAM, and flash memory.
Yes, it does.
It can be a bit confusing to keep them all straight.
Sure, let's break it down.
Okay.
DRAM, or dynamic random access memory.
Uh-huh.
It's the most common type of memory used in computers and smartphones.
Okay.
It's relatively inexpensive, but needs to be constantly refreshed to retain data.
So DRAM is like a short-term memory bank that needs constant reminders.
Exactly.
What about SRAM?
SRAM, or static random access memory, is much faster than DRAM
Okay.
because it doesn't need to be refreshed.
Uh-huh.
However, it's also more expensive and takes up more space on a chip, so it's typically used for smaller, high-speed tasks.
Okay, and then there's flash memory, which is what we use in SSDs and USB drives, right?
That's right.
What sets that apart?
Flash memory is non-volatile,
Okay.
meaning it retains data even when the power's off.
Mm-hmm.
It's like a long-term storage vault for our digital lives.
From short-term memory to long-term storage, it's amazing how these different types of memory all work together to keep our digital world running.
It really is an intricate dance of data.
But there's one more area I'm curious about: optoelectronics.
Okay.
The book describes it as the intersection of electronics and optics.
Right.
What does that mean in practice?
Optoelectronics is all about using semiconductors to generate, detect, and manipulate light.
Okay.
It's a field that encompasses everything from LEDs and lasers to solar cells and fiber optic communication. It's a really exciting area.
Okay, let's start with LEDs.
Sure.
They're everywhere these days.
They are.
What makes them so special?
LEDs are incredibly energy efficient and have a long lifespan.
Okay.
They work by converting electrical energy directly into light.
Okay.
And the color of light, it depends on the semiconductor material used.
So we can thank semiconductors for all those vibrant colors we see in our screens and displays.
Absolutely.
What about lasers?
Oh?
They seem much more intense and focused.
They are. Lasers use a different process called stimulated emission,
Okay.
where photons of light trigger the release of more photons, all in phase with each other.
Okay.
This creates a highly focused beam of light
Uh-huh.
that's used in everything from barcode scanners to laser surgery.
From everyday gadgets to cutting-edge medical technology,
It's amazing.
lasers have certainly made their mark.
They have, that's for sure.
And then there are solar cells, which are becoming increasingly important as we shift towards renewable energy.
Right, solar cells are based on the photovoltaic effect,
Okay.
where sunlight striking a semiconductor material knocks electrons loose, generating electricity.
Wow, so it's harnessing the power of the sun.
It is. It's a fascinating process.
We've covered so much ground in this deep dive.
We have.
From the fundamental building blocks of semiconductors to their incredible range of applications.
It's been quite a journey.
It's been an eye-opening journey.
It has.
What stands out to you as the most impactful takeaway from this whole deep dive?
For me, it's the sheer ingenuity and creativity that goes into this field.
Yeah.
Engineers and scientists are constantly pushing the boundaries of what's possible with semiconductors,
Yeah.
leading to innovations that shape our world in really profound ways.
I couldn't agree more.
Yeah.
And Cracking the Code of Semiconductors
Mm.
does a fantastic job of capturing that spirit of innovation
That is.
and making these complex concepts accessible.
Yeah, it's well written.
I highly recommend it to anyone who wants to understand the technology that underpins our modern lives.
I agree. It's a must-read for anyone who's curious about the past, present, and future of electronics.
Well, that wraps up our deep dive into the world of semiconductors.
It does.
Thanks for joining us and for sending in such a fascinating book.
It was my pleasure.
Until next time, keep exploring and stay curious.